A lot of times when people take math classes, they hate talking about theorems, but you are going to love this one. I don't want to spoil it. I don't want to spoil it, so I'm scrolling up. Before we get into this theorem, I need a small definition. A feasible region is bounded if, if it has edges in every direction. Can you draw a circle that contains the whole thing? Otherwise, it's unbounded. So in our first example, our feasible region looks something like this. It was bounded, right? I can draw a circle that takes the whole thing. It's bounded. But if I didn't have the negativity constraints, or the non-negativity constraints, if we had these same lines, but we said it could be positive or negative, well, now it's unbounded. Because any circle I draw, right? Well, it still extends way over here even. So I can't draw any circle that has the whole region. This is an example of something that's unbounded. We're not really going to be solving unbounded problems. There might be one or two that kind of pop up, but we won't worry about them too much. And let's look at this theorem. This is a great theorem. If a solution to a linear program for a bounded region occurs, so if a solution for this type of program occurs, it's going to be at a corner point. A corner point specifically of the feasible region. So that is nice. If it's bounded, right? For bounded regions for a linear program. And what that tells us is there's only a couple options here, right? Let's draw the feasible region. It says if there's an optimal, it's at one of these 4 points. That's so much nicer, right? We just got to check 4 points. It's so much nicer than the method that we were kind of trying to do earlier. This theorem's so convenient. We only have to check 4 points and we can find the maximum. So we guessed that the maximum would be close to 193 basics. Knowing where the optimal has to be, you can probably guess. It was 195 basics and no premiums. But you could also check maybe 120 basics, 50 premiums, or maybe 110 premiums. The maximum's probably not going to be at 0, 0 unless we're losing money from creating these. Okay, but these are the only 4 options. Really nice theorem. Okay, and that's how we'll solve these. We'll just graph feasible regions and then check at each of the corners. And this is actually true for any dimensions. We're looking at 2-dimensional problems, 2 variables. In 3 dimensions, now our lines become planes. And the intersections are like vertices on like a 3-dimensional like cube or polyhedron. And it's still true for those corners as well, like the corners of a box, if you will. And 4 dimensions, we can't graph it anymore, but it's still the same thing. Actually, there are ways to graph things 4-dimensionally, and in reality, a lot of linear programs that are solved are like 100-dimensional linear programs, which is not as bad as it sounds. Of course, you're never going to graph that, but they're not too bad. We use computers though. All right, so here's some instructions for solving a linear program. Why is this squiggled? Let's get rid of this squiggle. Here's some instructions for solving a linear program. Now, if you're feeling bold, the book tells you to try this one now. I think we might want to go through it together, but if you're feeling bold, see if you can follow the instructions on this one. Okay. Here, in this try it now version, steps 1 through 3 have already been done. Steps 1 through 3, right? These are just creating the linear program. I'm going to write LP for linear program. And then the next steps are solving it. So in example 2, notice that it already tells us what the linear program is. So we only have to do steps 4, 5, 6, and 7. All right, so let's do it. Step 4 says graph the feasible region. That's section 3.2. So if you need some refreshing on how to graph these, section 3.2 is the way to go. All right, everything's positive, so we're only going to look at a graph that has positive numbers here. To graph this, it's usually easiest to solve for y. So this first one becomes y is less than or equal to 9 minus x. And the second one becomes y is less than or equal to 15 minus 3x. So I'm going to count by 2's here. This is our x-axis, this is our y-axis. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So the first one has a y-intercept of 9 and a slope of -1. It goes down 1, right 1, down 1, right 1. Again, down 1 unit, right 1 unit. Not always the same as down 1 box, right 1 box. And this is what this one looks like. It's solid because it's less than or equal to. And we're looking at everything under that line. We're only looking in the first quadrant here. Only looking at the first quadrant because of these requirements, which are pretty common. Now we can also graph a red line. Let's have this one be red. 15, can we draw 15? 12, 14, 15 is like right here. And then down 3 units to 12, right 1 unit. Down 3 units to 11, right 1 unit to 2. Down 3 units to 6, and so on. Like so. Graph this. Whoa, wait, what did I do? This is not a line. I messed up. Down 3 units to 6, right 1 unit to 3. Okay. Down, and this is where they're supposed to cross, I think. Yep. So this has both points. This is the downside to graphing things by hand. But this is where both points intersect, or both lines intersect. And then again, down 3 units to 3, right 1 unit to 4. Down 3 units to 0, right 1 unit to 5. And now hopefully they should all lie on a line. I really cannot draw straight lines. If you're solving things graphically, using some sort of straight edge would be nice. All right, and then everything under this line. And our solution, our feasible region, is the green area. That was step 4. Graph the feasible region, the blue area. Step 5, identify all the corner points. You can either do this graphically if it's obvious, but in my cases, it's not always obvious. So you can also solve the system of equations. That's section 2.1. So let's say you say, Jason, I don't trust your graph. Let's solve the system of equations to find it out. Step 5. So when are these two inequalities equal? All right, we know some of the corner points already, right? One of the corner points is going to be this blue point over here. I'm going to make it a black point. 0, 9, one of them. Another one's down here, 0, 0. Another one's right here. We know that one. That's 5, 0. But we're not exactly sure whether this is the point that it looks like or not. Okay, so let's solve to make sure that I'm guessing right. Because graphical solutions are not very reliable when we graph by hand. So when are these two things equal to each other? Well, when their y values are equal to each other. One has a y value of 9 minus x. One has a y value of 15 minus 3x. We're curious when they are the same. That's the intersection of these lines. We can add 3x to both sides to get 9 now plus 2x. And we can subtract 9 from both sides to get 2x is equal to 6. That gives us that x is equal to 3. So y is 9 minus x. Y is 6. So this is the point 3 comma 6, which is what I thought. So that was step 5. Step 6 is test all corner points with the objective function. Choose the winning. In this case, the winning one is going to be the maximum. We want the biggest one. What is the biggest profit here? Well, it's P. I don't know if P stands for profit here. What's the biggest one? So we'll make a table and say, what are our points? And what is P? So we'll have to check each corner point. Sometimes a lot of times 0, 0 is going to be a silly thing to check, but sometimes it'll actually be the winner and it'll surprise us. So don't forget to check it. 0, 9, 3, 6, and 5, 0. And again, a lot of times this one's going to be the winner, but not always. And in fact, when we were looking at basic and premium products, it actually wasn't the winner. We're looking for the biggest one. So plug 0, 0 into here and see what you get. So let's do that in a different color so it doesn't overlap. P is 14 times 0 plus 9 times 0. Oh, this P is going to be 0. P is 14 times 0 plus 9 times 9. This P will be 81. P is 14 times 3 plus 9 times 6. That's 42 plus 54. 96, I think. 54. Maybe it's 96. And the last one, P is going to be 14 times 5 plus 0. That's going to be 70. Which one's the biggest? The maximum is when x is equal to 3. This is our last step. Write your answer in the context of the problem. This problem doesn't really have any context. We'll say the maximum, the max value of P is 96. And it's when x is equal to 3 and y is equal to 6. That's how we'll write our answers. It'll be easier when we do one with context. So that's what it looks like. And I thought I was doing this in the next video, but let's do another one. This is going to be a long video. So a lot of times the hardest part is getting here. That'll be steps 1 through 3. So let's read the problem. A health food business would like to create a high potassium blend of dried fruit in the form of 10 fruit bars. Okay, so we want 10 fruit bars. Maybe we'll write that down. It decides to use dried apricots, which have, apricots are going to have 407 milligrams of potassium, which is K, per serving. And dried dates, which have 271 milligrams potassium per serving. The company can produce its fruit through in bulk, that's weird wording, for a reasonable price. Dried apricots are going to cost $9.99 per pound. And that's about 3 servings. Dried dates are going to be $7.99 a pound. And that's about 4 servings. This is getting complicated. All right. The company would like the box of bars to have at least the recommended daily potassium intake of 4,700 milligrams. All right, we want at least 4,700 milligrams potassium and at least 1 serving of each fruit. All right, at least 1 serving of each fruit. In order to minimize cost, that's important, minimize the cost, how many servings of each dried fruit should go into the box of bars? That's a lot going on. We wrote down what we thought were the important things. That's a lot written down. Let's go into the step-by-steps. Step 1, define the variables. Usually the question being asked gives a good hint to what these should be. What is the question being asked? How many servings of each dried fruit should go into the box of bars? That tells us what our variables should be. It wants to know how many servings of apricots and how many servings of dates. Those can be our X and Y. All right. So that's how we're going to start. Let X equal the number of servings. You could say A for apricots, of apricots. And Y is going to be the number of servings of dates in one box of bars. Great, that's step 1. That's honestly an important part of the problem and usually one of the harder ones. Step 2, write the objective function in words and an equation. Remember, the objective function is what we're trying to maximize or minimize. We're trying to minimize the cost. Okay? We're trying to minimize the cost, so we already wrote that in words. Minimize. Now let's write it with variables. Let's call it cost C. What is the cost? Careful. It's not $9.99 times X. Right? It's $9.99 for every pound. It's $9.99 for 3 servings. So how many is it for 1 serving? X is 1 serving of apricots. It's going to be $3.33, right? $9.99 divided by 3 is how much it costs per serving. We're going to assume here that we can have partial pounds of purchasing. Otherwise, it gets more complicated. And then again, likewise, it's $7.99 for 4 servings. Ew, gross. So that means it's going to be $7.99 divided by 4 per serving of dates. That's our cost function. We're graph on Desmos. I'm not going to make you grab this one by hand. That would be pretty fun though, right? $7.99 divided by 4. They couldn't have just made it $8 and we could write a 2 here. Oh gosh. Okay. I guess I'm the one who made these notes. I'm responsible for taking the problem as it was given in the book. Okay. So that's our objective function. Okay, I'll make a little note here in red. Right? Is our objective function. We found it. That's important. Getting the linear program itself is usually the hardest part. I'm not going to simplify this. You could. You can always ask me if you're unsure whether you need to simplify. Now let's write the constraints in words and an equation. So in words, we already did that, right? Our constraints are right here, right? This is our objective function. These are our constraints, the requirements. We need at least 4,700 milligrams of potassium, and we need at least 1 serving of each. How can we write those as inequalities? So the total, right? The total amount of potassium has to be at least 4,700 milligrams. How much potassium is there going to be? Well, and it's going to be 407 for every serving of apricots and 271 for every serving of dates. Great. And then we need at least 1 serving of each. So that's going to be X. I'm leaving some space here intentionally. X should be at least 1 and Y should be at least 1. So you can see now that we've used almost everything. The only thing we haven't used is the fact that there are 10 fruit bars. And I actually paused real quick to double check that we don't need to use that. And sometimes information gives like extraneous, the problem gives extraneous information that you don't need. And yeah, because it doesn't ask us ever, like, do we need to do something per bar? It just wants a full box. The fact that a box has 10 fruit bars doesn't really matter. So these are our constraints right here. So a lot of times we deal with 4, but here there really are only 3 that we have to worry about. So that's step 3. And now that we have our actual linear program, right? This is our linear program right here. Now it's just like the previous problem. We're going to graph it on Desmos, check the corner points, and see the winner. So we'll graph the constraints to give our feasible region. 407x plus 271y I already forgot. 271y greater than or equal to 4,700. And then x and y have to be at least 1. Okay, when we do that, we get this region. Let's zoom in a little bit. Okay, so these are all greater than signs. So it should be in this region right here. So a lot of times before we were dealing with less than signs and maximizing. Here we have greater than signs, this white region here, greater than signs we want to minimize. So where are the corners of this feasible region? Here, this is an unbounded region. But because we're minimizing, there'll still be a solution and we can still check it with corner points. Okay, it's technically unbounded because we could make this box have apparently infinitely many fruits. Apparently these bars can be any size that we want. But these are the only options for us here. So let's check them. And it's okay that it's fractional. We can have fractional servings of fruit. So this first one is going to be when there's 1 serving of apricots and about 15.8. Let's round. Okay. So again, let's look at an XY. And again, if you did want to give like a rough picture, a rough picture is something like this and this and this, and here are our points. And this is our feasible region up there. If you did want a picture, this is what the picture looks like. You could label it, but you don't have to draw this one by hand. Our points are about 1, 15.8. Another point is about 10.9, if you round, 10.9, 1. Let's check what the cost is at each one of those points. And the winner here is the lowest cost. Okay, so we'll look at the point, x, y, and the cost. First point is going to be 1 of apricots, 15.8 of dates. Second one is going to be 10.9 servings of dates, and 10.9 apricots and 1 serving of date. So we plug those into our cost function. I'm going to use Desmos for that one too. So our cost is 3.33 times x, which is 1 in the first one, plus 7.99 divided by 4 times y, which is 15.8. The first cost is $34.89. That's an expensive cost to produce this box of bars, 10 bars. The cost of the manufacturer is about $35. These must be big bars. I don't know. And the other one is 10.9 and 1. So this is 1. 10.9. The other one is $38.29. So there we go. This is our winner. So we answer and say the minimum cost for a box of bars is $34.89, and it has 1 serving of apricots, and about 15.8 servings of dates. Okay, for the box. So each bar would have 1/10 a serving of apricots and 1.5 servings of dates. This is our answer. Expensive box and very date heavy. This question's not asking about what tastes good. This question's asking about what saves money. I don't know if anyone's buying these date bars though. Anyway, let me know if you have any questions and enjoy. We got more videos and more practice.